Hello everyone, this is CHF 301, Atomic and Molecular Structure and Bonding, Workshop Lecture 5, which is on calculations involving photoelectric effect. I'm Andrew Tehemi Chowa. I lecture physical chemistry in the Department of Chemistry, Benue State University, Makurdi, Nigeria. This lecture is meant for my third year chemistry students, as well as other students worldwide who are interested in the questions I tackle on this channel. If you have any questions or any comments, you can send those to me using either my university email address or my Google email address. Alternatively, you can leave those as comments in the comment section of the video, and I'll do my best to respond. Today's lecture is on calculation of the kinetic energy and the speed of ejected electrons in photoelectric effect. Also, we're going to calculate Planck's constant, work function, and threshold frequency from photoelectric effect data. So after the lecture, I expect you to be able to calculate the kinetic energy and the speed of electrons ejected in photoelectric effect. I also expect you to be able to use photoelectric effect data to obtain Planck's constant, work function, and threshold frequency of the experiment. So our first question says, what is the kinetic energy and speed of electrons ejected from surfaces of libidium by light of wavelength 700 nanometer if the work function of libidium is 1.14 electron volt? So to obtain kinetic energy of ejected electrons, we are going to substitute the given data into an expression that relates the work function and kinetic energy of ejected electrons, and then solve for the kinetic energy. We are then going to use the kinetic energy, the value of the kinetic energy, to solve for the speed of ejected electrons. So from the expression kinetic energy equal to H, which is the Planck's constant times frequency minus the work function, we can further write that kinetic energy is equal to H, the Planck's constant times the speed of light divided by wavelength of light, where C all over lambda represents the frequency minus the work function. So the Planck's constant H has this value, the speed of light has this value, the wavelength of radiation is 700 nanometers, and we can write this in terms of meters as 700 times 10 to the power of negative 9 meter. We simply substitute 10 to the power of negative 9 for nano. The work function is 1.14 electron volt, and we can write this in terms of energy because we know that 1 electron volt is equal to 1.602 times 10 to the power of negative 19 joule. So if we multiply 1.14 electron volt by 1.602 times 10 to the power of negative 19 joule per electron, then we can find the value of the work function in joule. That gives 1.826 times 10 to the power of negative 19 joule. We substitute all of these values into this expression, and it gives us this. This is Planck's constant, this is speed of light, this is the wavelength, and this is the work function in joule. This evaluates to 1.0 times 10 to the power of negative 19 joule. So from the expression kinetic energy is equal to half mv squared, we write this. We make V sub E, which represents the speed of the ejected electron, the subject of the formula. We know that the mass of electron is 9.1 times 10 to the power of negative 31 kg. Speed of electron, we don't know. So we substitute the mass here, the kinetic energy which we found in the first part of the question. We substitute it there. 2 times, that's the kinetic energy. We write this in terms of kg, meter squared per second squared, that represents joules, and divide by the mass of the electron, which gives 4.7 times 10 to the power of 5 meter per second. So here is the self-test question to check if you understood the first part of this workshop. Light of wavelength 200 nanometer is irradiated on a metal surface whose work function is 4.3 electron volt. Will photoelectric effect occur? If no, why? If yes, why as well? If photoelectric effect occurs, what will be the kinetic energy, the Diplock wavelength, and the speed of the ejected electrons? Our second question says, the following data were obtained in a photoelectric effect experiment involving potassium. Here is wavelength, here is kinetic energy of ejected electrons. Determine the Planck's constant, work function, and threshold frequency of potassium. This problem can be solved by plotting a graph, and we can plot the graph in 2 ways. The first way involves plotting the kinetic energy of ejected electrons against the frequency of ejected electrons, and this is in line with this mathematical formula. Kinetic energy equal to h times v minus phi, where h is the Planck's constant, v frequency of ejected electrons, phi work function. That gives a linear graph where the intercept on the kinetic energy axis gives the work function, and the intercept on the frequency axis gives the threshold frequency. However, because the data is given in terms of kinetic energy and wavelength, we've got to convert the wavelength into frequency, and we do that by dividing the speed of light by the various wavelengths, and before plotting the graph of kinetic energy against frequency. The second way or method involves plotting the kinetic energy against the inverse of the wavelength in line with this mathematical formula. In this case, the slope is the product of the Planck's constant and speed of light. So by equating the slope to h times c, where c is the speed of light, we can directly divide the slope by the speed of light to obtain the Planck's constant. Intercept on the kinetic energy axis gives the work function, and then the intercept on the inverse of wavelength can be used to find the threshold frequency. We are going to go for the first method, which involves plotting the kinetic energy of ejected electrons against the frequency of ejected electrons. Here is the given data, wavelength against kinetic energy. We obtain the frequencies for the various wavelengths by dividing the speed of light by the wavelength, and that gives these as the frequencies. So this is the plotted data, the data we are going to plot, kinetic energy against the frequency of ejected electrons. Here is our plot, kinetic energy against the frequency. This gives a straight line which we can take the gradient, or rather slope. So the slope, which represents the Planck's constant, can be obtained in this manner. That gives 6.71 times 10 to the power of negative 34 joules second. This can be compared to the literature value of 6.626 times 10 to the power of negative 34 joules second. The intercept on the kinetic energy axis is the work function, and it gives 3.61 times 10 to the power of negative 19 joules. The intercept on the frequency axis, which represents threshold frequency, is 5.5 times 10 to the power of 14 per second, which is hertz. Yes, so here is the second self-test question. It says determine the value of the Planck's constant using the following photoelectric effect data. This is wavelength. This is kinetic energy of ejected electrons. When you've solved this problem, you should have a value that agrees very closely with the literature value of Planck's constant. If you find this video helpful, I invite you to subscribe to my YouTube channel. Ring the bell so that you'll be notified when new videos are uploaded. Like, comment, and share. Thanks for watching. The link to the PDF version of this lecture can be found in the video description. If you have any questions or any comments, you can send those to me using either my university email address or my Google email address. Alternatively, you can leave those as comments in the comment section of this video on YouTube, and I'll do my best to respond. Bye now.